All right, here we are. So we'll pick up where we left off. Come on in. We waited for you. Hey, we're not like that. It's good to us. So we're starting with protozoan eventually. Oh, I was gonna wear my just throw on the replace the Steelers thing with the King sweatshirt, and my wife looked at me and goes, "You're not wearing that." That's why I changed. And she was even critical of this. She goes, "This shirt has a stain. It's old. I'm not going to meet the king." She goes, "If you do, you're getting a new shirt." So that's why the change, and it's okay. I've got to do laundry. She's got to spend. She's spending the next 5 days at her mom's, which is not great. So me and the dog and the two cats, but that'll be right. We'll all be okay. So that I have enough. So that way she can watch the Super Bowl at home, and I can watch unlimited sporting events for the next couple of days. It's not a problem. I can live with it. Okay, so that's the backstory. I'm happy to see everybody who's here, and I actually started with this with the other group today because I know we had left off with it, and this is the end of Cowan's chapter, which is the eukaryotic, and it's just a little intro because we really look at this again when we do the diseases. But these are the mostly water or land-based simple animal-like cells called protozoans. So they're and that's what the name is. You see, first animals. Most of them are not troublesome. They're just there, and they're doing whatever they're doing environmentally. So the big difference. There are some really significant pathogens. Bad news: malaria. To me, the second most common sexually transmitted disease, Trichomonas vaginalis. Very severe food foodborne diarrheal diseases, all from this category. So it's not innocent or innocuous, okay, whatsoever. We aren't going to deal with ecto or endoplasm or anything like that. And yeah, perhaps a primitive nervous system, uh, not nearly as well developed a cell as ours, but still a eukaryotic cell. We categorize them based on how they move around. So when you looked at pond water in high school and they had things that were spinning around or moving for Vorticella and rotifers and all that stuff, we characterize them by how they move. And we even named a movement for that called amoeboid movement for an amoeba, which is a relatively large, it has pseudopods or false feet. So it'll kind of like it'll flow the cytoplasm to here and it'll shift it to here and it'll look like it's almost like extending it. And we see a lot of that when you start to look at white blood cells and macrophages. They work by amoeboid motion. They sort of scooch like a baby would on the floor, would be the best way to describe it. And yeah, and the membrane is critical, and the cell shape is relatively constant, except for the amoebas, which change, and they're relatively small. As you can see, we're talking about even the largest one. That's something you might see with the naked eye, but by and large, most of them are in the micrometers, the very, very small measurements. They're like us. They eat everything. That's what heterotrophic means. They digest organic, just like we do, proteins, fats, sugars, break them apart, use them as either building blocks or an energy resource. That's what heterotrophic means. For the most part, there's a lot of similarities from us. They scavenge, okay? They can scavenge on bacteria or algae, so maybe to some extent that's useful. If you and we're not going to, but you can look closely at them and see these little grooves that look like a feeding structure. So it's a little closer to us than say a bacteria or through the membrane. And as you can see, they can live on, and this is where the problem is. So when we look at Trichomonas vaginalis or malaria, malaria is in the plasma. Trichomonas vaginalis utilizes things within the genitourinary system to be able to move. They do require moisture, which is an important thing. There's a lot of areas where they are, and they can survive relatively extremes. So they're versatile. The two phases, and this, I don't ask the question on a test. This is one of those in the back of my mind goes, This is an NCLEX type question. This is a licensure question. What's the infectious form of a protozoa in this trophozoite? That's the feeding stage. That's where they infect you. The stage where it goes, it's not as tough as an endospore to get rid of, but they're tough. One of the hardest things to get rid of when you're sterilizing something, other than bacterial endospores, are these protozoan cysts. That's what veterinarians look for in fecal samples because it suggests to them that they've had some kind of infection that has to be dealt with. So that's when they do a stool sample. Is whenever you bring your cat or your dog in, and they want to take a look at that stuff, that these are a dormant stage that can be really very difficult to deal with. So that diseases get spread that way from the stuff going around surfaces, but when it becomes active, the trophozoite is that, and perhaps the one we're going to see similarities with this as we look when we get to the clinical stuff, which is in the second half of the course, and they're just showing it to you here. So some by themselves are only trophozoites. So it's bad news and good news. The bad news is they're constantly active and infectious. The good news is they can't hide. And this would be one. So it's not, to me, human papillomavirus, trichomonas vaginalis, herpes. Big three when it comes to the number of cases that we deal with. You'll find, thankfully, there's treatment for this that's very effective. That's the good news. But the bad news is the treatment doesn't lead to any long-term kind of immunity. If you get it once, you can get it again or again, etc. And because of the fact there's no cyst stage, it has to be by intimate contact, and extraordinarily common. These are cysts. So if maybe where you reside, we're not in. I grew up in the New York megalopolis. Okay, everybody had city water. Nobody had a well. Out here, plenty of people as you get more rural as we head into. Less so here in Allegheny, and more so as you get out into Butler and Beaver and the other counties, Orange County and all the way up Crawford, Venango, etc. A lot of well water. When wells interact with septic systems, you have well water, you got a septic tank. Bad news. Or an animal fouls the water, which is frequently the case. Then you end up with entoamoeba histolytica, which is called amoebic dysentery, which is different than bacterial, and giardiasis. Okay, and that's diarrhea for days, long time, big problem. My kids, my three little ones, stayed with my secretary when they were like infant 3 and 4. Okay, because they're 3 years and 2 weeks apart. She had well water where she lived. She and her husband lived, and unfortunately, all got sick. Not her fault. I mean, just the wells that serviced her and her family's area because they all lived in the same area. Oh, a mess. So all the kids had to be on medicine for that. We'll go into that. And thankfully, my kids survived, and they're very annoying. Do you know where my daughter is now? She and her fiance. Oh, we're doing a getaway weekend. They texted me last night. We're going to Fort Lauderdale. I'm just telling my wife I'll get back to her. Okay, so that in itself. So I said, have a safe trip, have a great time, and other things. Why wasn't I invited? Do you want to have a good time, Dan? So all of those are part of it. So you'll see these. We'll deal with these kinds of things. Here, I mean, these are ones you're going to deal with. Leishmaniasis. And we see this. These trypanosomes, leishmaniasis, are things we touch on. These are very often because we have a relatively pristine, it's all about the water supply. We end up if you go to equatorial Africa, if you go to less advantageous country, the animals use the same water. There's animal urine, there's animal, this is how it's spread. If you have an open cut or a sore, so the water supply is very significant. If you go on, I know the nursing students still go on basically a mission they used to go to Nicaragua. Now we're going someplace else. They go to Ecuador. But
The trip,
yeah,
I think they're in London.
yeah. I mean, there's a trip where they go in South America. They used to go to Central America, and I think we are going someplace else. Pardon me? Ecuador last year. Yeah, gotcha. Dr. Ross does that. Yeah, he and I live in the same rough neighborhood, Cranberry. So I often we'll see him out and about at Costco and places like that. My one of my stepsons is friendly with his sons. Uh, so all of that type of this isn't spread that way. Oh, this is all about mosquitoes, malaria, and malaria. I'll say it 1,000 times. The largest killer in equatorial or what they call sub-Saharan Africa. Toxo. If you'll hear about that. Toxo is something that when they talk about it, it's carried by animals, but we get into contact with our contact with animals, particularly for those of us cats. Where do you find it? Cat litter. Okay, so I mean, this is why you tell if someone thinks they're pregnant or might or trying to get pregnant, they shouldn't be changing the cat litter. Or we had 8 cats. Guess who changed all the cat litter? For years. It was so 8, 8. Now I only have 2 cats. So that's everything. We're not doing worms. Well, I have to share with you about that. Now to get to the stuff for today. That killed 10 minutes. All right, we're good. I shouldn't say it that way. Okay. This next chapter is chapter 6 in your textbook, Cowan. I use some illustrations, particularly in some of the information from Nestor, which says Anderson chapter 4. I have that cooked up over here as well. So I kind of back and forth it a little bit, which works for me because I'm so used to it, and we'll begin. So it really we function on how they grow here, what limits their growth in certain areas like temperature, availability of moisture, availability of oxygen, and particularly focus on something in this chapter called the bacterial growth curve, which is something that is done in a laboratory, but we extrapolate information from that. We gather information about how it impacts living systems. Most of this is straightforward. This is a little bit reminiscent of what many of you did in the first third of AP1. So you talked about essential nutrients and macronutrients and minerals and vitamins. These guys, and I don't spend a lot of time. This starts with that. Essential. Doesn't just mean important. Essential means in living systems and biology must be acquired by diet. You guys should all should remember what essential amino acids. There, depending on the author, there is either 8 or 9. What does that mean? We can't make them. We have to acquire them through our diet. Once we have them, we can make all the 20. We can make those are the ones we can't make in our systems. That's what makes them essential. We get that from eating proteins from animal-based sources. So it doesn't have to be meat per se, or fish per se, or poultry, or drinking milk. It's in all of them. Those are referred to as a complete protein. So the folks who have trouble with this, not so much vegetarians because they can do dairy, but vegans because they don't eat any animal products. And therefore and if you're not eating animal products, there aren't a lot of products that are vegan that are complete proteins. That's why beans and rice, combination of a legume and another seed. The only legume that I know of, and there may be more, that's used a lot in cultures that don't eat a lot of meat or other things, so they eat a lot of fish, is tofu. That's a legume that's a complete protein. That's why tofu and soy-based products are so abundant. It's a very useful legume, whatever your feelings about it. I happen to like tofu. Mapo tofu. Oh, yeah. Hot stuff. Oh, whoa. You don't like hot, spicy food? Remember our house, if you're not sweating, you're not eating. Oh gosh, you really have to expand your palate. So these are macronutrients. For us, it's the big four plus two. So for us, for bacteria, same deal. Big four plus two. Carbon, hydrogen, oxygen, nitrogen. Difference for us, calcium, phosphate. Well, calcium, phosphate. That's why there's so much. For bacteria, yes, phosphorus, but sulfur. You should know that distinction. So you have the major macronutrients, carbon, hydrogen, oxygen, and these are by no means, these you would call these minor, but I wouldn't call them micronutrients. To me implies things that you and I basically look at as minerals. Okay, vitamins and minerals. The difference between a vitamin and a mineral, vitamins are organic, minerals are not. And any of them, they are essential in the sense that we do have to acquire them through our diet. So when you look at the back of a label for ingredients, particularly if you have allergies or you have certain, food limitations or on a special diet, always look at that stuff. Okay, because we need to have a certain amount of it. And most people who eat a balanced diet get all that stuff. If you don't, you should take a vitamin supplement because most times have vitamins and minerals or whatever. I think so. The micronutrients, very tiny amounts or trace elements. That's all that stuff. I mean, a lot of enzymes require and a lot of proteins require these to form properly or enzymes to work properly. So the most famous of these, and many of you may or may not have studied as yet, iron vis-a-vis hemoglobin. You can't make hemoglobin without iron. Iron forms the core of what's called heme, and because of the iron surrounded by organic stuff, that's where the oxygen sits, which your blood carries all over the place. So, and iron levels are important. Some people, they're comparatively low. Mine are comparatively low. But I've had 2 ulcer surgeries, so they've been low ever since that. So, and then there's different nutrients depending whether they're, and if you don't remember, I'm not going to ask you, the difference between organic means covalently bonded carbon that has either carbon to carbon and carbon to hydrogen units that are there. That's the minimum for organic. So if you have carbon dioxide as a classic inorganic, meaning it's even though it's covalent carbon, it's not to another carbon, it's to oxygen. And indeed, that's what photosynthesis does. It takes inorganic carbon dioxide and basically through the magic of chlorophyll and sunlight and water creates carbohydrates. It's staples or what we call fixed carbon. So it affixes carbons to one another. So, and we go from there with regard to creating a variety of organic nutrients. Carbon and hydrogen items, usually the product of living things. I mean, even methane, which is natural gas by definition, is organic. Certainly not consumable, but it's that basic one you studied in AP1 with the C with the 4 H's. Remember that? I was a chemistry major. I love that stuff. So we're not going to rebuild the wheel or do AP1 again. Thank you. Okay. If you want to, we can. Don't lie. And of course, water. So just like us, 70% water, okay, mostly organic compounds. There's the chomps that are there, CHONPS, the way I just remember it, okay? And you don't need a whole lot to make a whole lot, as you can see there. And they go through all of this. You certainly don't have to know anything on this chart. Not interested whatsoever, but it gives you an idea. And it's very similar, though not exactly the same as, let's say, one of our cells. So the big distinction in this early part of the chapter is what are called heterotrophs. That's us. Technically, we are called chemo-organo-heterotrophs. We eat organic chemicals, carbs, proteins, fats, things with nucleotides, and basically we separate, as I said before, we chop them up as building blocks, and when we chop them up, we release energy that we convert to ATP. So our energy comes from carbon compounds, and our building blocks come from carbon compounds that you and I ingest, whether you're vegetarian, vegan, omnivorous, whatever you are. Doesn't matter. Same place. That so hetero means different things to grow with. Auto self grows. So auto plant. So the core of photosynthesis is it makes its own carbon compounds by quote unquote fixing carbon dioxide, inorganic carbon dioxide as its carbon source, and it uses its energies from the light. So we call that a photo autotroph is really the full name. And for our purposes, they fall into two. Our studies here are either heterotrophs or organoheterotrophs, same thing, or autotrophs, which it means photoautotrophs. And basically that's regular bacteria and then photosynthetic ones. That's really all you have to know. It's not the only ones. Microorganisms are very exotic, as you will see. Okay, so we again we get our energy from chemicals and our carbon from chemicals. So hence chemoheterotroph or organochemoheterotroph and photoautotrophs. Here we get light for energy and carbon dioxide is the carbon source. Look at some of these oddballs. Chemoautotrophs. So they use methane. Okay, these are effectively a rock eater. I mean, hey, I don't like that granular stuff in my food. Something you're chewing something kind of crunchy. Yeah. What'd you have to? I had gravel today for lunch. Oh, delightful. I had pumice, organic lava. Now, sometimes I've been in some cafeterias that have been bad. I think they've improved them over time. We had a weird cafeteria in school. They kept bringing the same pudding out. Stood up to a spoon. The type with the skin on it. You seen that? You had to be in high school cafeterias back in the '60s. It's okay. No, no association whatsoever. So you can see some of these they are weird what they eat. Okay, so that's us, the chemoheterotrophs, whether they're parasites, but you have different ones who use light and chemicals. There's a lot of variations that are there. So I don't want to go into any of those because they're not really that important to us. So, and saprobes, the only reason for that definition, that's yeast and fungi effectively live off of debris or dead organisms. And when you talk really, and we spend a lot of time conversing about parasites. Parasites are, by definition, something that lives off of living stuff, us, or ourselves, or a bacteria itself, and so damages it. It basically takes its energy and what it needs to survive from something living, and in the process does damage. And it could be as tiny and as relatively simplistic as a virus to as complex as a worm. It could be on ecto or inside endo. You're going to see that we deal a lot, particularly with these. Viruses, by definition, are obligate intracellular parasites. They can't grow outside of a host. One of the deadliest of the sexually transmitted diseases for years till we started to see how to treat it, syphilis, only lives inside. Once it's outside, it doesn't survive. We still can't grow it. Leprosy, another one that only is inside, spread by very, very close sustained contact. Okay, not quote sexually transmitted, mostly physically transmitted would be the way to describe it, perhaps respiratorily transmitted. But still, there's no way to cultivate it so we could identify it. It's a real problem. And then it just talks about these, where they come from, and I never do any of this stuff. Things you need to review. I don't know how you remember it from your earlier courses. You should familiarize yourself again with how movement occurs across a membrane. By far and away, the driving force concentration increase. You have a high concentration or low concentration gradient, things move. You don't have to impart energy. If you have to move against the concentration gradient, if it's difficult and you have to impart energy now, it's active transport. So living things try to do non-energy means. They try to use things that do not require ATP. We use ATP to create concentration gradients and then benefit by the energy. That's the proton motor force Krebs cycle, whether you study it or not. Push a whole lot of hydrogen ions, and we actually magnify their effects as they come back through to generate large amounts of ATP. So we spend a little to make more. It's like an investment, and you get lucky and it clicks. That's right. So to me, the driving force is concentration gradient. Most common one that we use is diffusion. Simple diffusion means if you move across the membrane without any assistance, it's either very small and there's an opening, or it's membrane compatible, oxygen and carbon dioxide. Classic simple diffusion. Two lining cells with a common, very not nearly as thick as this, membrane between them, with a common layer between them, and the oxygen and carbon dioxide. And the beauty of the movement is the oxygen can move one way and the carbon dioxide the other way. It doesn't matter. You have 16 things moving at once, some in the same direction, some across. Do it almost instantaneously. Like as soon as you inhale and bring oxygen, that blood is coming in contact with it, even through the membrane in your lung and the membrane around the capillary where the deoxygenated blood is instantaneous. Just like you've ever seen blood. What color is blood come when you see a hemo in a tube that you're taking blood out? It's not dark, it's red right away. There's a little bit of oxygen still in that tube. You see a difference in arterial blood than comes out. So higher to lower. All the other factors may contribute, but concentration gradient is the key issue. Sometimes the particles are too large, so you have to enable them. We call that facilitated diffusion. So facilitating means there's a transport channel. If it's a pore, it's always open. Okay, so it's a permanent. What they call that channel motion. If it is a gateway of some type, when we imply transport channel, we mean always open. If we say transport protein, it indicates that something contacts it to open the door, so to speak. It may be just those molecules coming in contact with it that allows it to move either in or out. Or it may be something else like insulin, basically creating a series of events that opens a door that lets glucose enter the cell. So you're not using energy directly, you're using the impact of the insulin and the chain of events that occurs inside to facilitate diffusion. There's always more sugar outside of a cell than inside of a cell, because as soon as sugar enters one of your cells, we convert it. We add a phosphate, and it's no longer glucose. It's glucose 6-phosphate. You don't have to know that, but we change it. That's that's sort of the magic way the body works. The one most of the students have the most trouble with, osmosis. No different than anything else moving across the membrane. But remember, we use the term solute and solvent. What we're studying here in micro, this universal solvent is water. So if I say solvent, I mean water. And by definition, stuff that's dissolved in water creates a solution. And the stuff that's dissolved are solutes. So in questions, it'll say solute to solvent. Understand that that number, whatever the accumulation, sodium, potassium, glucose, proteins, doesn't matter. If you add all those up, they're all solutes. And in living systems, there's a fixed ratio of those solutes to solvent. So and osmosis is the same thing. If you've got a vessel that has, it doesn't matter what the particles are, 4 particles, and an identical vessel that has 12 particles, let's say, proportionately, they're the same size, not 12. 4 water here, filling out 4 particles to a year versus 12 to a year. So osmosis works, so there the concentration of water is greater. So water would go from here to here and balance it out. That's osmosis. So most of the time, particles move one way, water balances it out. So it's the same thing, watering a plant. So we give it a lot of water, and the plant doesn't burst because it's got a cell wall. You're going to see that. So they're just showing you motion that occurs here. This is the classic experiment. So in a bacteria, let's say, or a plant cell, whatever you want to represent it as, when you put it in an isotonic solution, solute to solvent ratio the same as it should as the interior. Like we use isotonic media, normal saline, D5W, lactated ringers, because they're isotonic. They have the right balance of sugars, salts, whatever is in there, to have the same solute to solvent ratio inside and outside the cell. You put that around an animal cell or a bacterial cell, no change. That's why we use it. Doesn't change. If we add hypotonic solution, it forces water in. It means it's almost like pure water, which it may be. And it will swell. In our cells, they'll burst. It's dangerous. So you can have water, and we every so often you see a case of overhydration or water toxicity, and somebody dies because, believe it or not, just from drinking too much water. I mean, what the other factors are, I'm not saying. Versus here, to a plant or a bacteria, has really negligible effect because you have a cell wall that holds it in place. The player that hurts both, and why we use dehydration, why we use curing, salt or sugars, or a combination, stuff around the bacteria to preserve it, or to pull it out of meat, or pull it out of fish, or pull it out of anything, is because it will suck the water out of the cell. And when it does, particularly if it's a bacteria, look what happens. It pulls the water out, the membrane pulls away from the cell wall, and the cell dies. That's how we destroy bacteria, by salting things and preserving things. The name we give it in cooking science is curing it. If it happens to one of our cells and we would ingest seawater, which is fairly salty, excessively, what the phenomenon is called crenation, crenation, and all that means is that the waters come out and its appearance looks like a little bumpy. They typically do it with red cell, red blood cell, and the red blood cell, like, rather than being nice and round, all of a sudden it gets very pointy. So it's almost like a spiky appearance. So that's a classic experiment. I used to do the experiment here in school. And they're just showing you the different channels. When we use active transport, it means energy, whether you're going against a concentration gradient, whether you're making vesicles and bringing stuff in or spitting stuff out. When you move membrane around it, which bacteria can't because they don't have internal, energy is required. When your white cells do macrophages, do endocytosis, they expend energy. So we're not going to do any of those things or any of those things. We're going to do this. This is the next part. These are the two things we have to do in the next roughly 15 minutes are the temperature levels and the oxygen level. This is really important because it dovetails into, by learning how they grow, we learn how to sterilize, disinfect, provide antiseptics. You know how they grow, being killed. The number one way we destroy bacteria, basically we look at pattern. We look at temperature as it increases going that way and how much it grows. People erroneously will look at a graph and say, oh, it must just do this. No, that's a bell curve, right? Normal distribution. You reach starting temp, let's say arbitrarily a death temp, an optimal temp, and that is exactly what temperature does not. Temperature changes and growth do not follow a normal or bell curve or Gaussian distribution, whatever term you want to describe. It starts that way. It starts from no growth, and as you increase the temperature, it goes up, up, up. It reaches its optimal, and then boom! Long cliff. That's the good news and bad news of temperature. Like the difference between the ground and point. Okay? Ground food tastes good, work food doesn't. Fine line between that. So you have minimal temp, pardon my handwriting, they call T optimal, best temp, and lethal. And for our cells, for bacteria, they are very close together. Temperature, you didn't do the immune yet. Basically, temperatures are friends, increases metabolic activity, activates our immune system up to a point. What's the normal temperature in our bodies? 37 degrees Celsius, 98.6. For every degree Celsius, 1.8 degrees Fahrenheit. 37 to 40, pretty short. That is 5.4 degrees. You go from being normal to 104. You go 2 more degrees, you'd be 107.6. Good, likely not so much. Very few people go up to 108. They become hypothermic. Enzyme systems shut down. Proteins. That's the beauty by pulling off the cliff. It's irreversible. And so we have 5 different levels that we utilize with this. So you can see this, that proximity, that's our enemy and our friend. I will show you on the other PowerPoint because it works easier. I think it's demonstrably easier here. And so this is what they're talking about. In temperature, they do the same thing. I'll show you the categorizations that are here. That's this. We have 5 levels that overlap. Living systems rarely have clear defined levels. So there's some bacteria that live better at room temperature, but still can survive at higher and lower temperatures. And there's overlap in these categories. The ones that concern us are not the extremes. The extremes, psychrophiles, you might find some in the polar ice caps, and maybe you find some in your freezer, and they really don't impact us. Psychro means cold. They love the cold. Okay. Hyperthermophiles, hydrothermal vents, volcanic caldera, some places ridiculously hot. Some places you couldn't even, much hotter than any place that you could possibly survive. They don't affect us. It's so they hyper, very high, lovers of very high temperature. It's these guys in the middle. And by far and away the most common one, and where the vast, vast, vast majority of our pathogens or disease causers are mesophiles. Meso means they like the middle. Okay. 35 to 40 degrees, so they work fine. They're still growing even when you get 104 temperature. That way. Many of them. Some are at the lower end, 35. Now you're 95 degrees. Well, where might we see something low like that? That's not inside of us. You all remember biblically leprosy. Leprosy, which is a bacterial infection, affects what we see, fingers and toes falling off, right? That's because those are acral areas and your temperature there is lower. So they flourish there, on your skin or within your tissue, as opposed to, let's say, in the middle of your abdominal cavity, which is body temperature. Get the idea why this all, we look at all this stuff. It's good stuff. Okay, there's an overlap between psychrotrophs, grow in the cold. The numbers are variable. As you can see, they go all the way down. Some of them go down here, close to freezing. Your refrigerator and mine typically is about 40 degrees okay, Fahrenheit. Right around, 3, 5, 7 degrees, wherever you want to set it, depending on your model and how accurate all the modern refrigerators, you can see it digitally. Okay, does that kill anything? No, it slows its growth. So the organisms at room temperature that would cause spoilage don't grow very fast. So things will stay there longer, not forever. Same thing with your freezer, not forever. There are different factors that affect the freezer. Some are even microorganisms. Mostly it has to do with ice crystals forming, and we'll get to that in our next unit. Because when we talk about freezer burn, it's not so much microbiological, it's sort of how you put things in and for how long. Okay. But in a refrigerator, put milk in the refrigerator. Is it going to last a month? I don't think so. Sooner or later, it's going to go. Okay. And you're going to get those, basically, the proteins denature, and you get curds and smells and yuck, like that. And on the other side, things that start to grow better when it gets warmer. We're not at any 70 degrees Celsius. My goodness. It would be 150 degrees. We can't survive. But down here, we might. Where might we come in contact with organisms here? Well, you go to a hot spring, but more commonly around here, you go to a hot tub. So a lot of people like to hang out in there. We have one on our deck, actually in our deck. Mojitos, midnight, hot tub. We do. We don't use it enough. It's no fun. The dog wants to get in. The dog loves it. He has never met a stream that he doesn't want to jump into. This is a four-seater that has room for really two people and not you, 75 pounds of happy. It's a big dog. I showed you the dog picture, didn't I? Yeah. Imagine that in your hot tub. So, why is refrigeration slows down the growth? Freezing, it'll go back and spoil if you don't, and then we get into the packaging. And here's the leprosy nugget that you saw there. The last nugget of these is oxygen for today. Oxygen, and this goes, this is why I did it in a sequence. This is for oxygen. And in order to be, you don't have to use the oxygen. Be around the oxygen, get those toxic derivatives like that. So you have to have some superoxide, this mutate, that is some catalyst. At least one or the other, and preferably both. And that's how we classify these different kinds of levels. You basically work with one or two in the lab. It's like this. There's an experiment, and I've done it at different schools. We don't do it here, where we take a tube and we inoculate it with different kinds of bacteria. Strict aerobes, facultative anaerobes, obligate anaerobes, microaerophiles, and aerotolerant. They're all about the air. You and I are, by definition, obligate aerobes. We have to have oxygen or we're going to die. That's what obligate means. So we only can grow or flourish in the presence of oxygen. We need oxygen to breathe. Okay? We have, in all those peroxisomes, those, at a minimum, those two enzymes to deal with those toxic derivatives like O2 minus, superoxide dismutase, and catalase. In the lab, you work with some of those. Bacillus subtilis is an obligate aerobe. Okay, there's certain kinds of staphylococcus. Most of the things you work with in the lab, okay, grow fine with oxygen, but they can grow great without it. They're called facultative. The word facultative means grows easily. The good thing is it grows easily, so you can work with it in the lab. The bad news is very hard to kill because it grows so easily. Tough time finding antibiotics. E. coli staph. Uses oxygen if it's there. If it doesn't, it'll ferment. So it produces the superoxide dismutase and the catalase. Ferments. If it doesn't, if it's using the oxygen, it's got something. If it's fermenting, it doesn't work. Obligate anaerobes, Clostridium, tetanus, botulism, C. diff. Okay, can't deal with oxygen. A lot of those nasty endospore formers in Clostridia are all strict anaerobes. C. diff lives in the colon. It's an anaerobic environment. They don't use it. They don't make it. So we can use oxygen to get rid of them. It's a good thing. When we talk about wound treatment, we'll talk about treating certain types of gangrene and similar conditions with in oxygen chambers, hyperbaric oxygen. Unusual, just a little oxygen. There are two that affect us clinically. One we talked about, that Helicobacter pylori is associated with ulcers or gastric carcinoma. It technically requires slightly less, between half of normal oxygen to 10%. That's 2 to 10%. Our normal oxygen here in the environment is 20%. So what they do is they grow only if you have limited oxygen, but you need some, and it produces some, as you might suspect, of each. And then the interesting one has nothing to do with oxygen. Aerotolerant, another name for them is obligate fermenters. They don't have an electron transport chain. They don't have any Krebs cycle. All they do is ferment. Because of that, they don't use oxygen. So it doesn't matter. But because oxygen's there, they have to have something to deal with it, and they have the superoxide distribution. Those are, as we conclude, the different ones that are there. So we went from temperature and all those changes, etc., that's there, to the gases that are there, and they just talk about it. And I don't really use it, just the equation that I did yesterday with more accurately balanced. And again, it's the same thing: aerobes, microaerophiles, facultative, etc. So that's everything. Thank you very much. Have a great weekend. Appreciate your time.